All right, class, so this is Mr. Eggleston again, and this is the Check Your Understanding, the CYU, for lesson 6.3, absolute value functions. Basically, we learned that from our discussion is that absolute value graphs are V's. They look like these things right here. All right, and that our goal, make it a little thicker, and that this graph has a special name for the point where the two lines cross, and we call that the vertex. All right, so the goal of this is really to figure out where's the vertex, and then you can just graph it, because the slope, unless there's a number in front of the absolute value graph, or in front of the absolute value, is 1. And this is what it's talking about right here. All right, the x minus h, when the number's holding hands with the x, that it will give you the x coordinate of the vertex. And then the plus k on the outside, not holding hands with the x, but blocked by the absolute value bars, that tells you how far up or down it goes. All right? So, when you look at 1a and b, you see that it's an absolute value graph, just absolute value, and then we subtract 2 on the outside. That 2 on the outside means the graph will shift down 2 units. You can see this if you make a simple table, or you choose 5 values of x is probably all we will need. So we'll go -2, -1, 0, 1, and 2. So when x is -2, absolute value of -2 is 2 minus 2 equals 0. Plug x equals -1, and we get the absolute value of -1, which is 1 minus 2, and that's -1. When x is 0, we have the absolute value of 0 minus 2, and that's -2. When x is 1, we have the absolute value of 1 minus 2. Absolute value of 1 is again 1, minus 2 is -1. And then finally, the absolute value of 2 minus 2 is equal to, the absolute value of 2 is 2 minus 2 is 0. So you notice that the numbers symmetric about this 0 point, 0 comma -2, are the same values. All right, that tells you the vertex is going to be at x equals 0, comma -2. So the vertex is 0, -2. Okay, so we're just going to plot that 0, -2 right there. And then when x is -1, we're at -1. When x is 1, we're at 1. When x is 2, we happen to be at 0, or -2. And when x is 2, we're at 0. You will find out that all these points, when we plug those x values in, will fall right along this dashed line. Okay? So this, connecting these dots, gives you the graph of the absolute value function. And there you go. All right. Notice it shifted the graph down 2 units along the y, because that's what this -2 does. This number's not holding hands with the x, so it moves it up and down. It's being blocked by this absolute value bar. So anyway, that's how you do it. Likewise, now look at the next one, which is going to be in orange here. Okay, it's the absolute value of x plus 4. Notice this number's holding hands with the x. That means this is going to move that absolute value bar graph along the x-axis. Matter of fact, x, absolute value of x plus 4, means the vertex is going to be located, remember the vertex is the tip of the V, vertex is going to be at negative 4. Now, you could put a little plus 0 on the outside, even though you don't need to. So the vertex is going to be at negative 4 comma 0. So we know that this graph is going to be right there, the vertex. Okay? And then we can make a table where we choose some x values. We'll center that table around negative 4, so I choose a couple numbers bigger and a couple numbers smaller than negative 4. And when we plug it in, you have the absolute value of negative 2 plus 4, which is the absolute value of 2, which is 2. So we know that when x is negative 2, 1, 2, we're at 2. We're there. When x is at negative 3, it'll be the absolute value of negative 3 plus 4. That equals negative 3 plus 4 is 1. So that's the absolute value of 1, which is 1. So we know that when x is at negative 3, we're at 1. You see how that forms a line, okay? When we go to the negative 4, that would be the absolute value of negative 4 plus 4, which is the absolute value of 0, which is 0. So you see we do get the vertex right there. When x is negative 5, all I'm doing is plugging it into the expression. Negative 5 plus 4, absolute value, that's the absolute value of negative 1, which is 1. And we're back here. And when x is negative 6 plus 4, negative 6 plus 4 is negative 2, absolute value of which is 2. So you see it's the same exact shape as previously, but the graph has just shifted to the left 4 units. Okay. Notice that the vertex, again, this is the vertex, now is at negative 4 comma 0. The vertex of the purple is going to be at 0 comma negative 2. And then they ask you for graph C, which is 3 absolute value of x. Okay. Easiest ways to make a table. This is going to be x, and this is going to be y equals 3 absolute value of x. We'll start at 0 in the middle, 1, 2, negative 1, negative 2. Absolute value of 0 is 0 times 3. It's still 0. So the green graph is sitting here at the origin. There's the vertex. Okay? When x is 1, absolute value of 1 is 1. So this is 3 times absolute value of 1, and that's equal to 3. So when x is 1, we're at 1, 2, 3. When x is negative 1, we're going to be at 1, 2, 3. When x is at 2, 1, 2, absolute value of 2 is 2 times 3. We're up here at 6. And likewise, negative 1, negative 2, we're up here at 6. And we have a graph. Oops, sorry, that's not 6. 6 is up here. That's why it was looking weird. Wow, Mr. Eggleston, let's get your act together. There is the absolute value graph. They all look like V's. And if you do not have a number that adjusts the slope of the line, notice the slope of this line. Here as we go over 1, up 1, 2, 3, over 1, up 1, 2, 3, over 1, we go up 1, 2, 3, and so forth. And we go in both directions, over to the left 1, up 1, 2, 3, over to the left 2, or actually, excuse me, Over to the left 1, we go up 1, 2, 3, and so forth. All right, so what the number in front does, like it said in the rules, the number in front is the slope of the lines. So the 3 equals slope. The slope of the A and B, there was a 1 that you didn't see, so the slope of those lines are 1, which meant we would go up 1 over 1, up 1 over 1, and we go both right and left to give us the V shape. Okay? Likewise, let's look at the table of value gives values for an absolute value function right here. Notice, the first thing you should notice, and let me change this, is at 4 we have one, we see that if we look right surrounding this 4, like right here at 5 it's 3, and that's 3 it's 3. That's 1 unit on either side of the vertex, or that's the point I circled, which turns out to be the vertex. And if we go over if we go over 1, 2, we're at 5. So this turns into 6, 5. And if we go over to the left, 1, 2, we have 2, 5. So you see, it seems like when we're the same distance away from that 4, 1, the output's the same. Where is the vertex located? Well, guess what? That's where the vertex is. It's because all the points will be symmetric about the point 4, the vertex point, which is 4, 1. So vertex is 4, 1. How do we know? Because all other points are symmetric about it. Means they're equally dispersed. You go over 1, you go up a certain distance to the right, go over 1 to the right, go up a certain distance, you'll go this. If you go to the left 1, you'll go up the same distance. Are symmetric. That's what symmetry is. Okay, that should be symmetric, not symmetry. Symmetric. What other values of x have the same output as x equals 1? This is a great thinking question. I could easily see this as a test question. Because if you look here, notice 1 is 1, 2 units away from, my bad. I almost said 2 units away from this vertex. That's equal to 1, 2 units to the left of the vertex, so there must be a point that's symmetric. It's going to be 2 units to the right. So what other values will have the same output as x equals 1? Well, x equals 6. Not 6. 1 is 3 units, so we'd have to go 1 more, and it'll be 7, and that would be equal to 7, right? And so it'll be at x equals 7. Because 7 is the same distance to the right of the vertex as 1 is to the left of the vertex. Which of the following is an equation for the absolute value function described? Well, we see that the vertex of this absolute value function is 4, 1. So we know that the equation is going to have y equals some a that we may not know, x minus 4 plus 1 on the outside. With that in mind, that tells you that this one's out of the question because they switched them, and this one's out of the question. The only two possible choices are I and IV, which is 1 and 4 in Roman numerals. So now, how can we pick the other ones? How can we pick between these? Well, we choose a point. I'll choose the point 1, 7. I'm going to see which of these of the two non-scratched off functions will give me 7 when the input is 1. So on I, if x is 1, that's going to be y equals absolute value of 1 minus 4. Okay, 1 minus 4 plus 1. That's equal to the absolute value of negative 3 plus 1, which equals 4. Okay? So when x is 1, we should get 7, but we got 4. So I can't be it. So there's only one choice remaining, and that would be IV. But let me show you why it's IV. IV, which is Roman numeral for 4, if you plug in x equals 1, you get, and we should get 7 out for y, you would get 2, absolute value of 1 minus 4 plus 1. 1 minus 4 is negative 3. And the absolute value of negative 3 is 3. So that's 2 times 3 plus 1. And does that equal 7? Well, yes. 7 equals 2 times 3 is 6. 6 plus 1, it equals 7. And thus, we were right to guess IV. Okay. And again, we got it by just eliminating two choices because they switched the x and the y on the vertex. That would be choice double I and triple I. And then we just plugged in a given point. I chose 1, 7 because it's on the table, but you could have chosen any of those points to verify which of the two equations works. And it turned out it was IV because it gave us that when x is 1, we're supposed to get 7 out, and we do. All right, that's it. Thank you. You have a good day.